Well, Connecticut Yankee Atomic Power Plant. This 600,000 kilowatt nuclear power plant went critical in the summer of 1967. Under the overall guidance of the Connecticut Yankee Atomic Power Company, Stone & Webster designed the plant in this building, their Boston office. They also undertook the entire construction. Westinghouse designed and supplied the nuclear steam system and the turbine generator. Engineers are developing a new nuclear vessel restraint. Engineering excellence and quality assurance come first. Then, reduction in construction cost and improvement to the construction schedule. These are the men who take the new concept and make it work. Stone & Webster has developed and owns many computer programs. These techniques were employed in many phases of the Connecticut Yankee plant design. For example, the pressure time transients following a series of hypothecated incidents in the protective containment which surrounds the reactor plant. On this peninsula, a nuclear power plant will be built. Water, isolation, reasonably good foundation conditions, and electric transmission lines were all available, but unfortunately no railroad. Here on the narrow floodplain between this broad river and a granite hill, one of the few available sites in Connecticut was selected. A private airport had already removed the virgin woodland. A turbine building will occupy the airstrip, and a nuclear containment replace the plains. The floodplain was not quite wide enough, so here at the rear of the site, the granite gneiss is cut away. This is the foundation for the first all-reinforced concrete containment ever built. The excavated rock face has been leveled, and reinforcing bars 2 1/4 inches in diameter are being laid for the 9-foot thick mat. The containment will be a right cylinder and dome, 135 feet in diameter by 190 feet high, lined with a vapor-tight steel plate. The construction that we see is not a concealed locomotive boiler to back up a nuclear plant. It is the enclosure for the in-core instrumentation conductors from the bottom of the reactor vessel to the readout equipment. In-core instrumentation of ion chambers and thermocouples will apprise the operators at all times of reactor core conditions, a most important factor in the continuing safe increase in nuclear plant capacity. A batch mixing plant on the site provides the concrete. Hour after hour and day after day, these buckets empty. Pour, vibrate, and pour again, as great care is taken to achieve a solid fill between these closely spaced bars. Concrete work continues through all weather, as the construction schedule for a structure of this size is no respecter of seasons. The bottom liner plate will be placed on top of this concrete-filled reinforcement. Circular bridging rings in the liner plate will join the vertical reinforcing bars above and below the liner, thus eliminating the seal welding of hundreds of bars that otherwise would penetrate the liner plate. These are the steel forms used for placing lift after lift of concrete in the 4.5-foot thick wall. As in all containments, pipe and electrical conductors must penetrate the containment wall. Special designs eliminate both vapor and radiation leakage. The equipment hatchway and double-door personnel opening will later occupy this access space. It is left open at this stage of construction to facilitate the building of the inner walls, which support equipment and provide shielding. Connecticut Yankee and Stone & Webster cooperated to arrive at a design which leaves sufficient room within these walls for laydown, refueling, and maintenance, thus saving many hours of shutdown time. The excavation for the circulating water intake structure takes place 30 feet below the river level, behind a temporary dike. We are now looking into the circulating water discharge tunnel for this plant and for a larger future unit. Long before the turbine generator is received, all possible progress must be made in constructing its pedestal, placing the condensers and raising the building walls and roof. For a while, this pedestal, the largest ever built for a tandem 4-exhaust turbine, dominated the landscape, with its tabletop 60 feet above the river. The containment polar crane has been placed on its supporting wall, and the liner goes up around it. Condenser tubes are ordinary inhibited admiralty, since the turbine plant that accompanies a reactor installation of this type need not particularly depart from a conventional design. The completed turbine building framing now encloses the turbine pedestal and the condensers. The reactor containment liner, made of 3/8-inch steel plate, continues upward. In cold weather, it is necessary, before welding, to preheat the steel. Machine welding is employed both inside and out. Every seam must be perfect, so in addition to quality control by radiography, every seam is die-checked and then covered with a welded-on steel channel for a tracer gas test. These are the means of ensuring 100% tightness, for the containment must later pass a rigorous leak rate acceptance test that even a single faulty weld could void. Before it is completed, this plant will have weathered 3 rigorous New England winters, but neither snow, nor rain, nor heat, nor even dark of night can keep these craftsmen from their appointed tasks. The reactor vessel, built of 11-inch thick steel plate, is on the shipping barge with its detached head. No railroad can handle a vessel of this size. From Chattanooga, down the Mississippi, across the Gulf, up the inland waterway, through Long Island Sound, and up the broad Connecticut, the reactor homes toward Haddam. The construction superintendent and resident engineer. The barge is hauled into a prepared slip by a winch, where it is sunk to rest on a firm bottom. The reactor vessel is secured to parallel ways, the starting point in the unloading operation. It is first jacked up, so the ways beneath may receive the proper coating of paraffin-type wax and grease, which perform their part in this unloading operation. The reactor vessel will be moved first by skidding, then an upending by a polar crane on the curved runners of the skid, and finally a lowering into place on its foundation. 5 lines from a crawler crane are enough to start the reactor vessel moving. With close attention, it can be seen to move about 4 feet per minute. A 40,000-pound pull moves the 850,000-pound load. On its 800-foot-long journey, the vessel is passing the turbine building. The skidways are picked up behind and laid down in front on a rolled crushed stone runway. About 15 days are required to complete this skidding operation. The vessel has been upended with the polar crane attached to the upper head flange, rolling on the curved ski. Early reactors were erected with rollers, blocking, tackle, pinch bars, and many men. Here, with a polar crane, a winch, and a skillful rigger, cost and untold hours of construction time were saved. When placed within its shields of water, steel, and concrete, the reactor vessel will be forever inaccessible. Here it is being insulated before lowering it to rest. Multi-layer metallic insulation and a stainless steel jacket are being installed on an around-the-clock basis. for from this time on, every hour counts. With the nearest railroad siding 10 miles from the site, a 58-wheel two-gooseneck tractor-trailer is used for hauling heavy loads. The 320-ton, 667,000 kVA generator stator is one of 8 oversized loads that were transported over local roads with less wear and tear than a cruise from normal traffic. The stator must next be raised to the turbine deck. Instead of a slow and expensive cribbing and jacking lift, the massive 320-ton stator is raised with an ordinary 125-ton turbine room crane, with the crane bridge blocked and with a second trolley temporarily borrowed from another plant crane. This demonstrates the desirability of designing with reasonable hoisting clearance. Little remains. The stator is over and into place 15 minutes from the time it left the truck. The high-pressure turbine rotor is being lowered into place. Off-color lighting does not do justice to these blades of polished stainless steel. The 3-element 4-exhaust turbine generator is 160 feet long and is expected to develop 650,000 kilowatts. A few years ago, 1 million pounds of steam per hour represented a large unit. For this turbine, every hour nearly 8 million pounds of steam at 700 psi are generated. Because of almost 100% steam generator efficiency and the interstage reheat, a net plant heat rate of 10,800 BTU per kilowatt hour is obtained. 4 220-ton steam generators destined for the Connecticut Yankee plant comes down the steep grade from the railroad siding. A brook crossing is reinforced. A local officer provides welcome assistance. The truck carrying the steam generator is backed into the containment hatchway, assisted by a cable from an outside winch using a reversing block. Note the reinforcement for the containment access hatch. Just as in a steel vessel, the material removed in an opening must be replaced in a surrounding reinforcement. The steam generator is upended on a sandbag cushion. This is shifted as the big crane lifts. Stone & Webster Ingenuity placed this steam generator on its foundation 5 hours after the lift started. The condenser circulating water discharges through this canal, about a mile downstream of the plant, since tidal effect from Long Island Sound causes reversal of flow in the Connecticut River. The containment is still going up. There is no manual handling of reinforcing bars, for these 60-foot-long bars weigh close to a half a ton apiece. The clearance between the inner and outer reinforcing bars is close. Nevertheless, it was necessary to leave 24 inches for men to work between the bars. Unlike the great iron ship with its riveted steel double hull, in which the shipbreakers found a skeleton, here the last man came out. Joining these close-spaced bars presented a problem, so Stone & Webster adopted the CAD weld process, rather than the more expensive and time-consuming arc weld. In this method, a forged steel sleeve surrounds the butted bar ends, and when poured full of a bronze alloy, grooves in the sleeve and deformations on the bars are keyed together. To obtain assurance that this type of joint would be wholly adequate, an extensive program was undertaken for testing full-size joints both before final design and during the actual construction. The public must be kept informed. Well-planned presentations and exhibitions assist immeasurably in maintaining a friendly atmosphere. The reactor vessel is now on its support and within its shield walls with the shipping cover still in place. Ready for insertion is the thermal shield, which is placed outside the core to protect the vessel wall from radiation damage. Developed in the late 1920s, the coated welding electrode is the unsung hero of modern construction, without which plants like this would not be possible. Inert gas surrounds the arc and, by excluding air, prevents a brittle weld. The reactor coolant pump, now being fitted up, is driven by a 4,000 horsepower motor. The four pumps circulate 270,000 GPM of 600-degree water at a velocity of over 40 feet per second. A final inspection is made of the interior of the reactor vessel, a survey for complete cleanliness, and a check of keys and guides, for the time has now arrived to start assembling the internals, which support the core in place. The vessel lining and all internal parts are stainless steel, such as this 90-ton lower core supporting structure, with its protruding guides for the in-core instrumentation. Placement must be precise. The thermal shield and the lower supporting structure, aided by the guide studs and spider, are lowered into the vessel. Meanwhile, outside structures are nearing completion. The plant office and turbine buildings have been completed. With the interior equipment now in an advanced stage of construction, the containment pushes toward completion. The dome liner has long since been finished. Lift by lift, the concrete dome advances upward. A unique strong-back construction braced against cured concrete, 2 lifts below, supports the curved forms for a new pour on the dome. The plant now starts to take on a finished appearance, with the containment dome nearly complete. Final cleanup and landscaping will be completed after the plant is in operation. The steam plant too nears completion. 4 24-inch main steam lines, each designed to carry 2 million pounds per hour, now cross the yard from the reactor plant to the turbine. Main steam stop-check valves are being fitted into place as a final step, preparatory to operation. Uranium fuel is now brought into the plant. Fuel consists of sintered uranium dioxide pellets in closed stainless steel tubes. 204 tubes make up a bundle, or fuel assembly, and 157 assemblies compose a core. A conventional plant of this size would require over 100 cars of coal per day, while only 3 trucks, like the one unloading, will fuel this plant for a whole year. This is the new fuel assembly storage rack. New fuel is readily approached for handling and storing. This new fuel is moved in reverse through the spent fuel handling system. An assembly is removed from the storage rack and then is lowered by an elevator into the spent fuel pit outside the containment. Cavernous pits and canals lined with stainless steel when later filled with water, will provide the shielding for the highly radioactive spent fuel. The fuel assembly is lowered into a hinged upender, which lays the assembly on a carriage bed. The carriage carries the assembly through a transfer tube into the containment. By reverse upending and grappling by a manipulator crane, the fuel is placed in the reactor core. Note the periscope for close observation of this loading operation. Precision indexed from above, the fuel assembly fits perfectly into place. This is not a nuclear glow, but rays from submerged floodlights, which provide illumination for inspection of fuel loading through binoculars or a periscope. The clarity is good, although 12 feet of water now cover the core. These are the tops of the steam generators above the charging floor, and the refueling cavity and canal above the reactor. When refueling some 12 to 18 months later, this canal will be filled with borated water. Then the manipulator will move this same fuel for several months' storage in the spent fuel pit before shipment to a reprocessing plant. The core loading is complete, and the core support plate and upper guide tubes are in place. These control rod drive shafts will extend into the latch-type drive mechanisms above the vessel head. The reactor vessel head is being placed. Final bolting follows. All of the production of the nuclear plant ends up in this turbine generator, and from it comes the electric power which justifies the existence of this plant. Most of the plant is unattended, but from this control room, every important operation can be monitored and regulated. Landscaping of this attractive structure is underway in fulfillment of the operating company's pledge that the natural beauty of this river valley would be restored. Each of the three companies responsible for this plant's performance has inscribed its insignia upon this hallmark. No longer a new concept, now generation, describes this latest addition to the growing list of Yankee nuclear plants, both under construction and in operation.